we go. Thank
Okay, you're welcome. Okay. Dr. Latif, before we get started, would you like to have a few words?
Thank you. Thank you all for joining this presentation by Rayhan. We are very proud of him, and I commend Dr. Ozaf for facilitating this process in partnership with Munster High School. We are very happy to have students coming here and working with our faculty and our other researchers so that they have experience and have interest in this kind of work. I truly appreciate all of you, and I commend all of you to make this happening within this unavoidable situation right now. So Zoom works. Thank you, welcome all, and I'll be watching the presentation. Thank you all. Take care.
Thank you, Dr. Latif. With that said, we go ahead and start with Rayhan's presentation. And then if there are any questions, he will be happy to answer. So Rayhan, are you ready to share your screen and start the presentation?
Yeah, it's my.
Okay, so we have an echo again.
There you go. I don't think the echo should be there anymore.
Okay.
Very good. Okay, cool. Is my screen again?
Can you see the slideshow presentation? There you go.
Good. Okay, so hello everyone. So my name is Rayhan Zaman, and I am the Munster High School intern at Purdue Northwest Engineering Training Program. So I am here today to show you my presentation of what I've been working on for this past semester, which is where I designed and manufactured an iris mechanism for a solar reactor. So before I begin, I wanted to start by thanking Purdue Northwest, especially Professor Olzop and Professor Zhao, for connecting with Munster High School and giving me the opportunity to take this class. I also want to thank the engineers at Purdue Northwest that helped to supervise my learning as I went through this process. Connor Feeney, Marcel Mojulu, and Kyle Toth. They really helped me to learn a lot about what I was working with and gave me the skills that I needed to know in order to be successful. I also want to thank Mr. Brad Doctor in Munster High School for having this class be available to high school seniors. And finally, I want to thank all of you for being here today to listen to what I've learned this past semester. So as we go through this presentation, I'm going to start by talking about the introduction and my motivation for why I'm doing this project. From there, I'll go into the computer-aided design of the mechanical iris that I made. After that, I'll talk about the 3D printing and the 3D visualization of the mechanism that I designed. And finally, I'm going to talk about a lot of the things that I learned throughout this past semester. So global warming is a huge issue in the world today, including the increasing temperature that the world's been gradually going through for the past 100 years. There have been an increase in storms, droughts, wildfires, and then along with that, the heating of our oceans due to the increase in the temperature of the earth in general has been causing many aquatic sea creatures to die, and our waters have been being polluted by it. Along with that, the North and South poles are gradually melting, of course, due to the increasing temperature of the earth. And that's causing increased flooding on many of our coastal areas. Along with that, many of the fossil fuel, non-renewable resources that our economy is so reliant on are starting to dwindle away. In a study from Our World in Data from 2016, we only have around 50 more years of oil and natural gas remaining in Earth's reserves, while we have only around 114 more years of coal reserves before we completely run out of them. So with knowing all of this, why am I studying solar energy in particular and not just all types of renewable energies? Well, several other types of energy sources are really good to diversify each of the things we're able to do with our energy sources. However, many of these renewable energy sources are limited to producing only electricity and heating of water. Solar thermal energy stands alone with its unique feature of allowing not only power and heat generation, but also being able to produce fuels like gasoline, diesel, kerosene, or even hydrogen. Solar thermal energy can also produce metals like magnesium, zinc, and silicon. Therefore, I want to study solar energy to make my contribution toward the research efforts in utilizing clean energy to produce fuels, metals, and electricity. So this image that I have up right now is an example of a solar reactor. So the solar reactor consists of two main features. The first feature is the iris mechanism, and the second feature is the reaction chamber. So you can follow my mouse here real quick. So the iris mechanism is this half-shaped oval right here in the cross-section image. So this is basically how sunlight is able to get controlled into the physical reaction chamber. And then in the reaction chamber over here, we're able to produce fuels, metals, and power. So even though the solar reactor is a very interesting mechanism, it has the light energy needs to be controlled in order to maximize the efficiency of the reactor itself. So I developed machinery to help to control the amount of light that enters the reactor at a given time. So here is an example of a very early design for an iris mechanism. So as you can see, it's mainly just a wheel and axle with multiple openings inside of it. So how this iris works is that by spinning the wheel on its axle, you can vary the amount of sunlight that enters the reaction chamber at a given time. So with this knowledge in mind, I decided to start producing my idea for my iris reaction, for my iris, which is shown on the right here. So the very top image shows these two hooks that are connecting with each other. And this is my original idea of how I was thinking of being able to increase and decrease the amount of light that enters a given reactor at one time. So each of these pairs of hooks is one circle, produces one opening size. So if you want to go to a smaller opening, you'll have to go to a series of hooks that are smaller. If you want to go to a larger opening, you'll have to go to a series of hooks that are larger. And to do this, you have to go either forwards or behind, depending on how far down or up you are in design. And that's sort of illuminated in this image right here. So the smallest hook opening is at the very left right here, while the largest hook opening is over on the right over here. So if you want to get to, say, this fourth opening over here, each of these series of hooks connecting between it would have to open up. So the first series would have to start by opening up, then the second, and then the third. And that would allow the fourth opening to allow light inside to the reaction. These last two images were my original ideas of how to stack each of these series of hooks on top of each other in order to allow different sizes of light to enter the reaction at once. So my original idea was to have a type of peg, which would be on the hook, which would be on each pair of hooks itself. And by opening it up like that, it would allow a lot of space reduction, and it would also help to allow more light into the design at once. So of course, through the engineering process, that doesn't always pan out like that. So after a lot of experimentation and design work, this is the exploded view of the final design that I came up with. So it's a series, so it starts as a base plate with a series of 4 pairs of hooks connecting that are on top of it. And each of these hooks open up at different intervals, depending on how much sunlight is needed to power the reaction. So if you look right here to a couple of the dimensions, the overall iris design is a total of 140 millimeters in diameter, with the inner diameters of sunlight that are allowed inside the reaction at once being 30 millimeters, which is associated with the red hook, 40 millimeters associated with the yellow hook, 60 millimeters associated with the blue hook, 80 millimeters associated with the green hook, and then 100 millimeters, which is the inner diameter of the base plate. So each of these plates are around 6.5 millimeters in height, with all five of the layers being a total of 32.5 millimeters. So here's a very quick demonstration of how my iris reaction works, which I made through a computer-aided design software called SolidWorks. And what SolidWorks does is it helps you to visualize a very early design process of something that you want to build. Here's a quick motion study that was made through it. So as you can see, if you want to go down to a larger opening, you have to open up the hooks on the previous section. So say you wanted to get to the yellow hook over here, you would have to open up the red hook in order to get there. So it would look something like this, where the red hooks will not interfere with the yellow hook, but at the same time, the yellow hook would be able to get light into the reaction chamber, allowing fuel and other resources to be produced. So this is a quick picture of me in front of Purdue Northwest series of 3D printers. So after I made my design in SolidWorks, I exported it into a type of file called a standard triangle language file, which is where you have a series, which is just where each one of your parts is represented as a series of triangles. And I was able to get the chance to 3D print my objects and make a real-life version of my iris. So the 3D printers that Purdue Northwest has are called the MakerBot Replicator Pluses. So this is a very common type of printer that can be bought on the market today. And it's really simple on how to use it. So all you need is, like I said, the standard triangle language file, or the STL. So when you go to your computer, or if you plug a flash drive with the STL file into a printer, it starts by downloading the STL into its actual mainframe. From there, you're going to have to load up the material that you want to use to print. In the case of the MakerBot Replicator Pluses, you'll probably use plastic, as it's the cheapest way to get these types of objects printed. From there, the MakerBot Replicator Plus scans the object, determines the path of printing, and then it starts to heat the extruder in order to melt the plastic so it can go from inside of the extruder onto the actual surface where the printing will happen. And then from there, you can just watch your print happen. So I have this really quick clip of a 3D printer in action. As you can see, it takes the path that it mandated through itself, and it goes through it, and it just sets down these very, very thin spools. So what the 3D printer does is, depending on how much fill you want to have in it, it'll continuously go over these areas and make many different triangles on top of your object until you get the whole piece made. And then from there, you'll have your 3D printed object. So finally, I wanted to talk about the 3D visualization of my iris. To do that, Purdue Northwest recommended me to use Unity Gaming Engine, which is a great way to visualize 3D objects. So here's a very quick visualization that I made through Unity. It's really similar to a motion study, as you get like a good view around the object. And then after that, you can see the object in action. So as you can see, it works very similarly to how the motion study showed the object, where for every series of hooks that opens up, then you can get access to the next layer of hooks. Thus giving you more space to work with and a larger opening to allow light into. And if you want to go backwards, say you want to go from the 100 millimeter opening to the 80 millimeter, you can just go to the very bottommost layer and you can just close it up. So some of the conclusions that I learned throughout this project. So I would say the main thing I learned is that even though solar energy is extremely abundant, as we see it every single day, it has a huge problem regarding its power fluctuation. So in order to solve that, I decided to learn some engineering skills to produce this iris that I made. So I learned how to use CAD drawings and a game engine software to follow the engineering design process. From there, I learned that the creation of machinery requires a design evolution until reaching a final concept. After that, I observed how 3D printing using a 3D printer can help me to understand if I need to improve my design a little bit, if there are any issues that I had. I also learned that with 3D visualization, it can help to view design concepts from a different perspective, which will allow improvement. And finally, I learned that an engineer's purpose is to find ways to fix and improve many of the issues apparent in machinery today. So I want to thank you all for coming here today. This really means a lot to me. And if you have any questions, let me know. Thank you.
Thank you very much, Rayhan. Very good. Are there any questions to Rayhan? I'm going to get started with first question. So, Rayhan, how did you feel when you saw that your creation of that machinery came alive through the 3D printer? Did you feel like, okay, this is like, you know, I'm a mini engineer that fathering this machine and it's coming alive from my brain to reality? How did you feel when you first saw that the result of your invention?
That's actually a really good question. So I have 3D printed objects before through different classes, but those are just like really small keychains that I could just like use as like accessory. But through this project, I had to be able to think of a different, like a physical item that would actually make a change in the world. And watching it get 3D printed and actually functioning when I was like actually making it and trying it out, it really made me happy because it just showed me that like, dang, I actually made this. Like I used my brain and I could produce this.
Very good. Are there any questions to Rayhan?
I have one question, Rayhan, to you. Based on the experience that you went through and that support that you got from your teachers at Munster High and from the faculty members at Purdue Northwest, what would you tell to your classmates, or what would you like for us to do to promote this opportunity to your classmates or students at Munster High?
That's another really good question. So we actually have 2 high school seniors this year that are actually going to be attending this program this semester. So this is their chance of getting a good insight onto what this program is and what they're expected to be doing throughout this next semester as they become interns for Purdue Northwest. In regards to like promoting this program and opportunities associated with it, I would say it's mainly just about like talking to friends saying, hey, I was in this program. I found it really enjoyable. I learned a lot about like engineering and a lot of the different design aspects of it. And it's just a really fun project overall where it's not like where a teacher tells you, okay, you have to build this. You're given this specification, this specification, this specification. You got to go build it. It's more like you're given free reign over how you can like deal with it. And I think just because of that, it gives you a lot more real world experience than any class could actually give you.
So with that said, I would like to wrap our session by thanking again Brad, which closely monitored everything and always kept in touch. And I also thank the Munster High School principal, Mike, for this good collaboration, which we're very happy with the start of, as of yesterday, the new spring program. And we would like to see more students coming in and more creative products coming out of this engineering program in collaboration with the Munster High School.
Thank you. I truly appreciate this a key partnership with Munster High School and Purdue Northwest, helping, mutually beneficial partnership, in fact, to encourage students in the STEM-related area and provide the research opportunities that we have at Purdue Northwest. And that's our commitment to this community. So I truly appreciate all the support from Munster High.
And we thank you as well. And sometime when Rayhan has an opportunity to tell you, he's done some other really neat things for Munster High School through Project Green. So he's an Eagle Scout, and he's done some cool things with Project Green that we're working on here as an interdisciplinary project. So hopefully he'll get a chance to share that with you at some point. Again, thank you for this partnership and working with our students.
Thank you very much, everyone. Have a great day.
Thanks.
Bye.